Hello students, welcome to the online lecture series of digital communication. We are studying unit number 3, that is random signal in noise. So before moving towards our today's lecture, let's have a quick revision that what we have studied in our last lecture. In our last lecture, if you remember, we have seen the characterization of wide sense stationary random process in frequency domain relationship. That is, we have seen the power spectral density. After that, we have seen the various properties of power spectral densities. Today, we are going to see that what is Gaussian process, what is central limit theorem, then what are the properties of Gaussian process, and what is noise and what are its classifications. So let's move on to our today's topic, Gaussian process. Before studying Gaussian process, first we will have a quick revision of Gaussian distribution, or which is also called as what? Normal distribution. Now this Gaussian distribution, basically it is used for what? Continuous random variables. It is perhaps the most important PDF in the area of communication. Well, the majority of noise process, observed in practice are Gaussian, and many naturally occurring experiments are characterized by what? Continuous random variable with Gaussian PDF. So the PDF of a continuous random variable having this Gaussian distribution is given by what? This is called a Gaussian PDF, that is small fx x is equal to 1 upon under root 2 pi sigma square e raised to minus bracket x minus m whole square divided by 2 sigma square, and x which is greater than minus infinity and less than plus infinity. So make it as equation number 1. So over here this m is nothing but what? Mean of the random variable, and this sigma square, it is nothing but your variance of the random variable. This Gaussian PDF, as I told, it is also called as what? Normal PDF, and the shape, this is the Gaussian PDF, and you can see from this figure that shape of this Gaussian PDF, it is what? Bell type, as shown over here. And this is a graph of PDF versus your small x. And you can observe from this graph, the Gaussian PDF is a bell-shaped function with a peak at x equal to m. You can see over here, this is the peak, whereas x equal to m. It nothing but it is corresponding to what? Mean value of the random variable x. Second, this Gaussian PDF has an even symmetry about the peak. You can see that this is x equal to m at this side and this side. It means this is m minus variance minus sigma and m plus sigma. So it is what? Symmetry about this peak. So therefore we can write it fx, which is of x is nothing but your m minus sigma, which is equal to f of x which is equal to what? M plus sigma. So you can see that this is the symmetry of left hand side and right hand side over here. Next, the probability of obtaining x, that is a random variable, above and below the mean value is equal to what? 1/2. So we can write it probability of x which is less than or equal to mean small m is equal to probability of getting this x which is greater than m is equal to what? 1/2. And the area under the Gaussian PDF is 1. So we can write it fx of x dx equal to 1. And one more thing, that the this is a point x1 and this is a point x2. This shaded region with this green color, it has been shown that it is a probability of obtaining what? X between x1 and x2. So the probability of obtaining x between x1 and x2 can be obtained by integrating the Gaussian PDF between the limits x1 to x2, limits x1 to x2. So therefore we can write the probability that p x is greater than x1 and it is less than or equal to x2 is equal to what? Integration from x1 to x2, integration of what? Fx x. What is fx x? It is nothing but your 1 upon under root 2 pi sigma square e raised to minus in bracket x minus m whole square divided by 2 sigma square with respect to this dx. Now by understanding this Gaussian distribution or normal distribution, now we would proceed to Gaussian process. So Gaussian process is an important family of your random process. So let the observation interval for a random process x of t, it is be t equal to 0 to t equal to capital T, and let us weight the random process x of t by a function small g of t and obtain a random variable capital Y by integrating the product of g of t and x of t over the interval 0 to t. So therefore the random variable y is given what? Integration from 0 to capital T, argument of this g of t and x of t dt. Make it as equation number 1. Now if in the expression for this y, the weighing function g of t is such that mean square value of the random variable y is what? Is a Gaussian distributed random variable for every value of g of t, then the process x of t is called what? Gaussian process. In simple words, we can say the process x of t is a Gaussian process if every linear function of x of t is what? Gaussian random variable. And what is Gaussian random variable? A random variable is called as a Gaussian random variable if its probability density function PDF is of the following nature. So it is given by f of y is equal to 1 upon under root of 2 pi sigma square e raised to minus in bracket y minus m whole square divided by 2 sigma square. Make it as equation number 2. We are using this equation from equation 1. Just instead of x we have taken a random variable y, so that's why we have written over here y. So again this m is nothing but your mean of the random variable y, and what is this sigma square? It is nothing but your variance. So the plot of this Gaussian PDF, it is shown in this figure. So you can observe that Gaussian random variable, it has been normalized to get the mean at m equal to 0 and variance sigma square equal to 1. So at mean equal to 0 we are getting the peak maximum value of this PDF. So if we will put m equal to 0 and sigma square equal to 1 in equation number 2, the following equation it would become what? F of y is equal to 1 upon under root of 2 pi, because sigma square over here it is a 1, e raised to minus y square m over here it is a 0 divided by 2 sigma square, but sigma is 1, so it is e raised to minus y square by 2. So make it as equation number 3. Now the advantages of this Gaussian process is that it is possible to obtain the analytical results because of many properties just we have discussed previously. It is exhibited by this Gaussian process, and the random process which is produced by the physical phenomena are generally such that the Gaussian module, it is appropriate to explain them. Here is a theorem called central limit theorem. Basically, it is associated with related with your Gaussian process. Now we will see how. Basically, this central limit theorem is used when the PDF of several independent random variable is to be operated. So the probability density function of a sum of large number of independent random variable, it tends to approach what? Gaussian PDF, as just we have studied, and that is independent of the probability densities of the variable. Now suppose if there are large number of independent random variables, so we are let us suppose if x1, x2, x3 up to xn are independent what? Random variables. Then we have taken another variable called as z. That z it would be equal to what? X1 plus x2 plus x3 plus x4 up to xn. Then the probability density function of this z, it would be what? That is fz of z, it would be what? Convolution of PDF of x1, which is convolved with PDF of x2, convolved with PDF of x3 and up to xn, that is a PDF of xn. So how to calculate the PDF, the resultant PDF of z? It would be what? Convolution of fx1, fx2, fx3 up to fxn, that is how many number of variables are there. So let us assume that x1 and x2 are two what? Random variables, and they have a uniform PDF as shown in this figure, that x1 it has a PDF and x2 it has a PDF. Then what would be the z? If two random variables are there, then z is equal to what? X1 plus x2. And what about the PDF of z? It would be what? PDF of x1 which is convolved with PDF of x2, that is fz of z is equal to fx1 of x1 convolved with fx2 of x2. So what would be the resultant? What would be the, how would be the PDF of z would be there? Then it would be like this one. So you can see from this figure that fz of z, it is nothing but your resultant PDF of two random variables x1 and x2. This is nothing but your PDF of random variable x1. This is a PDF of random variable x2, and this is a resultant PDF that is of z, which is PDF1 which is convolved with PDF2, and you would get PDF of z, that is x1 plus x2, and the PDF of z is equal to PDF of x1 convolved with PDF of x2. So over here you can see this amplitude 1 upon 2x1. It is ranges from minus 2x1 to plus 2x1 because it ranges from minus x1 to x1. Similarly minus x1 to x1. So this range, it would be what? Minus 2x1 to plus 2x1. So this is your resultant PDF of z. Now we have assumed two random variables. Now in next figure, this one you can show it. Over here there are uniform PDF of random variable x1, uniform PDF of random variable x2 and x3 as shown in figure. So their convolution, that is of f of x1 convolved with fx2 which is convolved with fx3, it is going to approach what? Gaussian PDF, as that we have seen in Gaussian PDF. So how it would look? So it would look like this one. See, this is a Gaussian PDF of bell shaped. So even there are for the sum of these three terms, the resultant approaches what to the Gaussian PDF. So if I am going to increase the more and more independent random variables and then they are added, then definitely their resultant PDF, it will be what? Gaussian PDF. So you can see that is a random variable x1. This is a PDF of x1, ranges from minus x1 to x1. Similarly, it is a uniform PDF to minus x1 to x1, PDF of x3 minus x1 to x plus x1. So what would be the resultant PDF? It is added. So 1 by amplitude, see 1 by 2x1 plus 1 by 2x1 plus 1 by 2x1, it would be what? 3 by 8x1. And this, what its range is, minus 3x1 to plus 3x1. So hope you understand this basic of central limit theorem. So we can say that central limit theorem is used for what? Providing the mathematical justification for using the Gaussian process as a model for large number of different physical phenomena in which the random variables involved is a result of large number of individual random events. So let xi be a set of random variables with I equal to 1, 2, 3 up to n. So let all these random variables, it should satisfy the following conditions. First, all the random variables, it should be statistically independent. First condition. Second is that all of them have the same PDF with mean mx and variance sigma square, as just we have shown in figure. So let the random variable xi, which is normalized in following way. What is the formula? Y of I is equal to 1 upon sigma cap in bracket xi random variable minus mean and I equal to 1 to n. So that mean of this random variable e of yi is equal to 0 and the variance of yi equal to 1. Then we can define a random variable vn such that vn equal to 1 upon root n summation I equal to 1 to n y of I. So the statement of random variable, the probability density function, this theorem it states that the probability distribution of the random variable Vn, it will approach normalized Gaussian distribution n 0 1. What is 0? Mean equal to 0, variance equal to 1 in the limit as n approaches infinity. As the number of n the random variables, it increases to a large value. So hope you understood the concept. Now moving towards the properties of Gaussian process. So property 1, it is if a Gaussian process x of t is applied to a stable linear filter, then the process y of t developed at the filter output is also what? Gaussian. This is property number 1. Now, in order to get the property second, let us consider the set of random variables or samples x of t1, x of t2 up to x of tn, which is obtained by observing a random process x of t at the time instant t1, t2, t3 and up to tn. Now, if the process x of t is a Gaussian, then these random variables are jointly Gaussian for any value of n. Then their joint PDF is completely determined by specifying the set of means as under mx of ti, which is mean, expectation of this random variable x of ti, and I is equal to 1 to n, that much of random variables. And the set of auto covariance function, it would be given as Cx tk ti, which is equal to what? Expectation of x of tk minus mean, that is mx tk at that particular instant, bracket x of ti minus product of x of ti minus mx ti, and k ranges from 1 to n. Then third property, it is that if a Gaussian process is wide sense stationary, then the process is also stationary in strict sense. We have seen the difference between what is wide sense stationary and strict sense. So now the last fourth property. Suppose if the random variables x of t1, x of t2, x of t3 up to x of tn is obtained by sampling a Gaussian process x of t at time t1, t2, tn, which are what? Uncorrelated, then that means if expectation of the product of x of tk minus mx tk, x of ti minus mx ti, it should be equal to what? It is equal to 0, where I is not equal to k. Then these random variables are statistically independent. So hope you understood Gaussian process and properties of it. So after studying Gaussian process, let's move to the next topic of our today's lecture, that is noise. So noise, in a general term which is used to describe an unwanted electrical disturbance which gives rise to audible or visual disturbances in the communication system and errors in the digital communication signal, which affects what? Wanted signal. So unwanted signal, it disturbs wanted signal. So noise is a random signal that exists in a communication system, and the random signal, since it is a random signal, so we couldn't represent with a simple mathematical equation. Now from this block diagram, you can see that how the noise are going to affect your messages or your information. That this noise is called external noise, which has been added to this communication channel, and at the receiver, whatever the noise it is there, it is called what? Internal noise. So this information, when it is transmitted to this receiver through this channel, it could be wired or wireless, free space, then there is a chances of adding your external noise. And at the receiver, there is called a internal noise. So they are going to affect our information. So what are the sources of noise? So the sources of noise, it can be classified in two categories: external noise and internal noise. Now what is external noise? So this type of noise, it is introduced in the communication medium, and often it comes from the sources which we don't have a control, or we have a little control over the physical environment. The next type of noise, it is called internal noise. So this type of noise are within the electronic equipment itself. They are called fundamental sources of noise or fundamental noise, because they are what? Integral part of the physical nature of the material that is used for making electronics components. So the two primary sources of external noise are what? Natural noise, and second one is what? Your man-made noise. Now what are the effects of noise? As from the block diagram you came to know that no message is received exactly as the sender intends because of the presence of this noise in communication. So as we came to know that noise, it could be external or it could be internal. So what are its effect? The effect of noise, when superimposed on an information bearing a signal, it makes the message to be partially corrupted, or it could be what? It could totally destroy your message. Next, the noise message can be avoided completely, but its effect can be reduced by filtering
or reducing the signal bandwidth. Noise, it could not be, we can avoid it completely. Noise constitutes one of the fundamental limiting factor in the performance of communication system, and it is going to degrade the system performance for both analog and digital systems. As we came to know that what are the sources of noise, that is internal noise and external noise. So what are the various, what is internal noise? It is, internal noise is created due to what? Random movements of electrons in electronic circuits. Electronic components in a receiver such as resistors, diodes, transistors are major sources of internal noise. What are the different types of internal noise? It could be thermal noise, short noise, transit time noise, or flicker noise. External noise it is called, which is called a man-made noise and natural resources. The noise, it comes from natural resources. Now, this external noise, it comes from the sources over which we have little or no control, as I already told. Examples like industrial sources, motors, generators, and from manufacturer equipments. Then it is called atmospheric noise, which came from natural resources, are atmospheric sources, or called static electricity. Now, what is internal noise? So, internal noise basically is generated by components within the communication system, and this is grouped majorly into two types, that is thermal noise and semiconductor noise. Again, in semiconductor noise, it is categorized as short noise, transit time noise, and flicker noise. Now, what is thermal noise, or which is also called as Johnson noise or white noise? Thermal noise, it is the result of random motion of charged particles, usually electrons, in a conducting medium such as your resistor. And this type of noise is generated by all resistance, that is resistor, semiconductor, then the resistance of resonance circuit, impedance, cable, etc. As you can see from this figure, that movement of electrons, it is going to form what? A kinetic energy in the conductor related to the temperature. As the temperature it is going to it, the more movement of electrons it is going to take place, the more kinetic energy they are getting it. So when the temperature increases, the movement of free electrons will also increase, and the current flows through the conductor, which gives what? Thermal noise. Now, the random motion of charged particles generate from this random currents or voltage called thermal noise, and the average thermal noise power, it is given as Pn is equal to K TB watts. Now, what is K? K, it is your Boltzmann constant, that is 1.38 into 10 raised to minus 23 joules per Kelvin. Then T equal to absolute temperature in Kelvin, and B, it is nothing but what? Bandwidth of noise measured in hertz. The thermal noise, it is also called as white noise, because as you know that white light, it contains all frequency. So white noise also contain what? See, equal weighting of all frequencies due to this its uniform spectral density, as we have seen this Gaussian noise. So similarly, it is also called as what? White noise. Then next it is called short noise. Well, short noise, it is a type of electronic noise that occurs in all the amplifying devices rather than in all the active devices. Short noise was originally used to describe the noise due to random fluctuations in the arrival of electrons or holes at the output electrode of amplifying devices. Hence, it appears as randomly varying noise current superimposed on the output. Short noise also occurs in semiconductors due to the release of charge carriers, and short noise is found to have a uniform spectral density for thermal noise. That's why it is also called white noise. The next type of noise is what? Transit time noise, which occurs in transistors, which is called transit time noise. So it is the duration of time that it takes for a current carrier such as hole or current to move from the input to the output. And the devices themselves are very tiny. So the distance are also very minimal. So at low frequency, this time is negligible. But when the frequency of operation is high, then the signal being processed is the magnitude. As the transit time, then the problem can occur. The next type of noise is what? Low frequency noise, or called as flicker noise. Flicker noise or low frequency noise is the one appearing in transistor operating at a low frequency below few kilohertz. So flicker noise is proportional to the emitter current and junction temperature. However, this noise is what? Inversely proportional to the frequency, and hence it may be neglected at a frequency above 500 hertz and above it. Therefore, it doesn't have, it's no a serious issue it is there. In the semiconductor devices, flicker noise is basically generated due to the fluctuation in the carrier density, and it is proportional to emitter current and junction temperature. Now, the next type of noise that we have seen, it is what? External noise. External noise, it has again one type that we call it as what? Natural sources. So in that natural sources, there is one type of noise called what is atmospheric noise. Atmospheric noise, also called as static noise, which is caused by lighting discharges in your thunderstorms or other natural electrical disturbance occurring in the atmosphere. And these electrical impulses are what? Random in nature. Hence, the energy is spread over the complete frequency spectrum used for what? Radio communication. Next, it is called extraterrestrial noise. Extraterrestrial noise, in that it first comes what? Solar noise. This is the electrical noise which is emanates from the sun. So under quiet condition, there is a steady state radiation of noise from the sun, and this results because sun, it is what? A large body at a high temperature exceeding 6000 degrees Celsius, which radiates electrical energy in the form of noise over a very wide frequency. Next extraterrestrial noise, it is what? Cosmic noise. Now this distant stars, these are also a part of suns and having high temperature. So these stars also radiate noise in the way as our sun it does. So the noise received from these distant stars is called what? Thermal noise, or it is also what? Black body noise, which is uniformly almost over the your entire sky. The next type of external noise is called what? Man-made noise. This is basically a noise produced by the mankind electrical sources such as your spark producing mechanism from industries, and it is usually more intense in industry and highly populated area. By man-made noise or industrial noise, it means what? Electrical noise produced by such sources as like your automobiles, aircraft ignition, electrical motors, switch gears, leakage from high voltage line, fluorescent lines, and other heavy electrical machines. Such noises basically are generated due to make and break process in current carrying circuit. So here it's all about the noise. So today we have seen that what is Gaussian distribution or normal distribution. Then we studied what is Gaussian process. After that we have seen that central limit theorem, and we have seen the properties of Gaussian process. Then we came to know about noise, that what is noise, which is unwanted disturbance which is going to affect our wanted signal. Then we have seen the types, the classification of noise, that is internal and external. In external we have seen that extraterrestrial and atmospheric noise. In internal noise we have seen thermal noise, also called as Johnson noise, short noise, transit time noise, and flicker noise. Here it is your assignment. So please note it down, this assignment. In next lecture we are going to study narrowband noise. For any questions, you can post it to my mail sharing on screen. So it's all about today's lecture. Thank you very much.